See, in the last module, we were in the middle of the energy equation. If you just go to the slides, I will just try to recollect from the slides. See, if we just see, we were bookkeeping the energy of the control volume on the left hand side, and right hand side heat transfer into CV by conduction, and rate of surface and body forces doing work on the control volume. So we got this equation coming back, we got this whole of this equation. Just I would like to mention here that we shouldn't be under the impression that the rate of work done by the normal stresses, by convention we have taken sigma xx outward. Depending on the problem, they can be compressive also. Here I have taken tensile, but they can be compressive also. It's just out of convention we have taken this, but depending on the problem, my sigma xx can be negative as well. We shouldn't be under the impression that all the time sigma xx is going to be positive, that is tensile. Now coming back, let's do the algebra. Now we need to get this back in terms of temperature. So let's expand these terms. So let's write rho d by dt E plus u squared plus v squared by 2 equal to k del squared t by del x squared plus del squared t by del y squared minus p. If I take as constant, I get del u by del x, next also del v by del y. Okay, next term, first term I have taken, minus of, now I have to keep u constant, u del p by del x plus v del p by del y. Remember, I just expanded these terms and written and taken p common, that's all. So one small step I have skipped, but I have told it orally. Plus, now you can't take anything common, you will have to write everything. So plus, you just go on expanding this, no rearrangement. U del sigma xx by del x plus sigma xx del u by del x plus v del sigma yy by del y plus sigma yy del v by del y plus sigma xy del v by del x plus v del sigma xy by del x plus sigma yx del u by del y plus u del sigma yx by del y. I just expanded these terms plus, let's call this, put all of this in one bracket, plus u fx plus v fy plus q dot triple prime. Whole of this equation, I am going to call this as equation A. We are going to come back to this equation. Why? Because I want to deduct this term and end up getting dE by dt. That I will do it through momentum equation. So let's recollect what did we get in the x momentum equation. I write x momentum equation, rho du by dt is equal to minus del p by del x plus del sigma xx by del x plus del sigma yx by del y plus fx. I am taking the momentum equation which was written in the Cauchy form, Cauchy's equation. Okay, so because that helps me. So now you multiply this with u, rho u du by dt is equal to, I can rewrite this, you see, rho d u squared by 2 dt, it is the same. If I differentiate this, I get u du by dt, correct, because 2 gets cancelled out. So you get is equal to, you have multiplied with u, so minus u del p by del x plus u del sigma xx by del x plus u del sigma yx by del y plus u f x. Okay. So now you can do the same thing for y momentum equation. I am not going to write and again multiply in one go. I am going to write it rho v dv by dt is equal to rho d v squared by t dt is equal to minus v del p by del y plus v del sigma xy by del x plus v del sigma yy by del y plus v fy. Let me add these two equations. What am I trying to do? If you recollect, I have this d by t u squared plus v squared by 2 term. I just want to deduct that. That I want to do through momentum equation. We are getting that there. So you get rho d by dt of u squared by 2 plus v squared by 2 is equal to, whole of this we have to write. Let's write that. Minus u del p by del x plus u del sigma xx by del x plus u del sigma yx by del y plus u fx plus, that is minus v del p by del y plus v del sigma xy by del x plus v del sigma yy by del y plus v fy. So let me call this equation as B. What am I trying to do here is that I am trying to deduct equation A minus B. I am going to deduct A minus B. So to get that A minus B, okay, so we have A here, okay, and we have B here. So I am going to, so if I deduct left hand side, so you have E plus u squared v squared by 2, here you have u squared by 2 plus v squared. So left hand side you are going to get rho dE by dt, that's it. Now right hand side, k term, nothing is there in the B, so you have the conduction term k del squared t by del x squared plus del squared t by del y squared. Let me just tell you, all the B of the right hand side will completely vanish. What is left out in A is what is not there in A, B. That's all we are supposed to write. So let's do that. So you get, you have minus P, this term is not there, P del u by del x, del v by del y is not there, but you have u del p by del x, v del p by del y will get cancelled out with u and v del p by del y. So you are left out with minus P del u by del x plus del v by del y plus of, you notice here u fx, v fy will get cancelled out and you are going to get cancelled out these terms u del sigma xx by del x. So what is left out is only the stress terms, that is which are coming as stress as first, sigma xx del u by del x plus sigma yy del v by del y plus sigma xy del v by del x plus sigma yx del u by del y plus q dot triple prime. So this is our equation which we have gotten as energy equation, okay, but still we have not arrived because E has to be written in terms of temperature. So but let me remind, first let me substitute in this equation what is for sigma xx. So sigma xx is equal to, before I do the E thing, sigma xx is equal to 2 mu del u by del x minus 2 by 3 mu del u by del x plus del v by del y. Similarly, sigma yy is equal to 2 mu del v by del y minus 2 by 3 mu del u by del x plus del v by del y, and sigma xy equal to sigma yx is cross velocity gradients because this is shear stress. So, del u by del y plus del v by del x. Notice xx all u in x, v in y, velocity is in the same direction, here cross velocity gradients, please notice that. So, now this term, what am I trying to do is whole of this term will be written as viscous diffusion term. There is a small algebra, I am skipping that, I am writing directly which you can work it out. Phi equal to 2 mu del u by del x whole square plus 2 mu del v by del y whole square, okay, because you see sigma xx is into del u by del x, so you will have to get whole square minus 2 by 3 mu del u by del x plus del v by del y whole square plus mu del u by del y plus del v by del x whole square. So, this is viscous dissipation term. So, now the energy equation I can write the energy equation as rho dE by dt is equal to k del square t by del x square plus del square t by del y square minus p del u by del x plus del v by del y plus, I do not have to write whole that equation because I have written that as phi. So, phi viscous dissipation term plus q dot triple prime. Now, only final thing what is left out is to reduce this dE by dt in terms of temperature. Let us do, how do we do that? So, we know that enthalpy H is equal to internal energy plus P by rho, correct. So, if I write dH by dt, if I take total derivative of this, I get dE by dt plus 1 by rho, that is I am taking 1 by rho constant and differentiating with respect to pressure, then I keep pressure constant minus P by, if I differentiate 1 by rho, I get 1 minus 1 by rho squared d rho by dt, okay. Now, dH by dt is equal to dE by dt plus 1 by rho dP by dt minus P by rho squared, let us stop here, d rho by dt. We know by conservation of mass, I have d rho by dt plus rho of del dot V equal to 0. So, that means d rho by dt will be minus rho del dot V. So, I can write this as minus rho del dot V is nothing but del u by del x plus del V by del y. So, let me write directly for dE by dt, dE by dt equal to dH by dt minus of 1 by rho dP by dt. This has become plus if I take it to the left hand side, sorry, left hand side, now right hand side is minus of P by rho del u by del x plus del V by del y. Let me substitute this in dE by dt in this equation. Let me call this as C. Substituting in C. So, what will I get? Substituting in C. Substituting in C, I get rho dH by dt, okay, is equal to k del square t by del x square plus del square t by del y square. Now, you see this term and this term gets cancelled out. Remember, I am multiplying with rho. So, if I have multiplied with rho, I will have only minus P del u by del x plus del V by del y, which will get cancelled out with this term. Okay, so I will be left out with only plus this plus dP by dt plus dP by dt. Now here there is a mistake. This dE by dt is equal to dH by dt plus this is minus 1 by rho dP by dt. This is correct, minus 1 by rho dP by dt. So when it comes to this side, it becomes plus dP by dt plus, yeah, you have phi viscous dissipation term and plus q dot triple prime. Okay, so you have, we will have to just substitute H is equal to Cp into T. So if I substitute that, I get rho Cp dt by dt is equal to k del squared T by del x squared plus del squared T by del y squared plus dP by dt plus phi plus q dot triple prime. Okay, let me just write this expanded version of dt dt. Rho Cp del T by del T plus u del T by del x plus v del T by del y is equal to k del squared T by del x squared plus del squared T by del y squared plus dP by dt plus phi plus q dot triple prime. Let us try to understand each term. What is this? This is convection. So how do I understand this convection term? So I take this example all the time. U del T by del x, I am entering the AC room. Let us say I am entering the AC room, that means I am moving in the x direction. I am the fluid element that is having temperature T, but I am moving with velocity U. So that is convective term. Now this is the unsteady term, that is del T by del T. What is happening? While I am entering, let us say I am hit with an ice box. So temperature is changing with time because instantaneously someone has hit me with the ice. So that is del T by del T. So that's how I understand this term. This is nothing but conduction and this is pressure work and this is viscous dissipation, or you can even say that work done because of normal stresses and viscous stresses, and this is volumetric heat generation. Okay, so these are the terms which we got by doing the energy equation. Now actually, if you just make the convective term 0, that is there is no velocity, let us say, what will this, let us say no velocity, no velocities, what will happen? Left hand side is 0, then right hand side will be k del squared T. What will happen to the dP by dt? There is no velocity, so that will also become 0. Viscous dissipation is 0, and you will, if you at all, if you have heat generation is there. What is this? This is nothing but my heat diffusion equation which we derived in conduction. So it's not necessary, if you teach convection first and then teach conduction, you perhaps don't have to derive heat diffusion equation. You can directly write heat diffusion equation from this equation. So this is, I mean, they shouldn't be thinking that the heat diffusion equation is different from this equation. It's all the same. It's just that we had not taken the velocities and the stresses there. So this is what we get by deriving the energy equation. So what we will do is, what we will try to do is, we will summarize all the equations what we have written so far. So that is, we have written, what is that we got? d rho by dt plus rho del dot v equal to 0. This is why conservation of mass. conservation of momentum, what do I get? Rho du by dt equal to minus del p by del x plus mu del squared u by del x squared plus del squared u by del y squared plus del squared u by del z squared plus del by del x of mu by 3 del dot v plus fx. This is the x momentum equation. Y momentum equation is rho dv by dt equal to minus del p by del y plus mu del squared v by del x squared plus del squared v by del y squared plus del squared v by del z squared plus del by del y of mu by 3 del dot v plus fy. That is y momentum equation. Z momentum equation, rho dw by dt minus del p by del z plus mu del square w by del x squared plus del square w by del y squared plus del square w by del z squared plus del by del z of mu by 3 del dot v plus fz, and rho cp dt by dt is equal to k del squared t by del x squared plus del squared t by del y squared plus del squared t by del z squared plus dp by dt plus phi plus q dot triple prime. So this was the summary, what all we did in the last 3 modules. We derived conservation of mass, conservation of momentum in the x direction. From that we directly wrote y and z direction, and this is the energy equation. So these are the 5 equations which we use to solve and get velocities and temperatures with the appropriate boundary conditions. So what we shall do is, we shall now do, or before we do that, what we can recollect is, what is this term? This term is nothing but inertia force. This is inertia force. We should be aware of what we are writing. And what is this? This is nothing but pressure force. What are these forces? These are nothing but viscous forces, and this is body force. Just little while ago we recollected that in the energy equation, this is the convection term, this is the conduction term, this is the pressure work, viscous dissipation, and the volumetric heat generation. So we now appreciate each term, what is the physical significance of each term. So now let us take up what is called principle of similarity. We shall start with principle of similarity. I will not be able to complete this in this module, but let's get started and let's take it up and conclude that in the next module. Principle of similarity. Okay. So in the principle of similarity, we shall write for steady and 2-dimensional flows. So we have the momentum equation here. We write this momentum equation for only the x momentum. For 2-dimensional, let's write that for 2-dimensional steady flows. 2-dimensional steady flows. So just to recollect, du by dt is what? Del u by del t plus u del u by del x plus v del u by del y plus w del u by del z. Okay. So steady 2-dimensional flow we are telling. So steady means this term would not be there, and 2-dimensional flow, this term would not be there. There will be no variations in the z. So you have the left hand side, you will get as rho into u del u by del x plus v del u by del y plus is equal to minus del p by del x plus mu del squared u by del x squared plus del squared u by del z squared, del y squared. Del z squared term is not there because we are not taking any variations in it is a two-dimensional flow in variations in the z direction. So you have del by del x of mu by 3 del u by del x plus del v by del y plus fx. Okay. So now what will I do is, I will have to non-dimensionalize these equations. So to non-dimensionalize that equations, what will I do is, I will write x star as, I will non-dimensionalize x with a characteristic length x by L, y star, that is non-dimensionalize y with length, characteristic length, u with u infinity, that is u infinity is, let us say, free stream velocity in case of flat plate or average velocity in case of flow in pipes. Okay. So then L is a characteristic length, you will take length of the flat plate in case of external flows or diameter of the pipe in case of internal flows. U star equal to u by u infinity, V star equal to V by u infinity, and P star equal to P by rho u infinity squared, and rho star equal to rho by rho infinity. What am I trying to do is, we will non-dimensionalize, we will represent this non-dimensionalize and see what non-dimensional number crops up when we non-dimensionalize this equation. Okay. So, and here when I do this, I am going to neglect body force. I am neglecting the body force. Each body force is going to give a different non-dimensional number, but for making a case simple, I will keep the non-dimensional, the body force is not there. I think we will stop this module here and continue this principle of similarity in the next module. And we realize that when we non-dimensionalize momentum equation, we are going to end up with a non-dimensional number, Reynolds number. When you non-dimensionalize energy equation, you are going to end up with Reynolds number, Prandtl number, Eckert number. So what is the physical significance of each of that? How do we get that? We shall do it in the next module. Okay.